Okay, well, you just mentioned my author, so I don't have to do that. Hey there. So we've already discussed multivariate schemes, so I don't need to. All right, maybe that's better. Maybe we don't need to go over the basic construction of multivariate schemes again. So we can just go right into the history of multivariate encryption. So if we focus specifically on encryption, the early history, I think there are three main schemes slash families of schemes of encryption schemes. So that would be C star, that's the original one. Triangular encryption schemes, so that would include things such as Moon Letter, which was also in the 80s, 1986, if you're familiar with that one, and HFE. And so these schemes are pretty much all broken. In fact, they are essentially all broken. HFE, you can find parameters to make it secure if you want, but it's not very efficient. So there's my statement. These are all essentially broken. If we look in more modern attempts, more recent attempts, we have ABC simple matrix encryption scheme. So we have a quadratic version of that and a cubic version of that. There was also a ZHFE, which was an attempt to get a high degree central map, but a version of HFE essentially. Extension field cancellation, we had that a couple of years ago. I think that was PQ Crypto 2016, if I remember correctly. HFE minus as a method of encryption. This idea, the first I heard of it was at PQ Crypto 2016 also. And then another even more recent attempt is SRP, which is the motivation behind this scheme. So again, for these schemes, the ABC simple matrix scheme, we came up with over the last few years a few different attacks on versions of this that caused the parameters to need to be changed. So surprising attacks there. ZHFE, we have a pretty strong attack on that also breaks some parameters. Extension field cancellation, not yet, but possibly soon. HFE minus, the last PQ Crypto, we came up with an attack on that. You can easily find parameters that avoid that attack, by the way, but still kind of a surprising attack. SRP, we completely destroyed that scheme. We really obliterated that scheme. And that's what we're basing our new scheme off of, interestingly. Many of these surviving schemes, not all of them, but many of them have this interesting property that the number of equations is roughly twice the number of variables. And this is an interesting idea. I guess the philosophy here is you have some more room for selection of interesting functions if you have a larger output space. And if you think about it, for encryption, all you really need is an injective map. To be able to invert an injective map, that's all you need for encryption. So you don't need to have this restriction that the number of equations is roughly the same as the number of variables. It can be vastly larger. The penalty for that, of course, is much larger key sizes. So there's a trade-off. But an interesting question is, can we have fewer equations, fewer than double the number of variables, and still have efficient key generation, encryption, and decryption? And that's what SRP really tried to accomplish. And that's what we're trying to accomplish with our scheme as well. Okay, so here is the basic construction of this class of schemes. This is not in the paper. I'm abstracting away. So I'm calling these star RP schemes, where star just stands for plug in your favorite primitive here. So the idea is to take a successful signature scheme that we know a lot about the security of, and most of these signature schemes have some point where you make a random choice of variables and then solve for other variables in terms of those. So the triangular signature schemes worked on this idea, oil, vinegar, rainbow, for example. And some of these we know a lot about the security of. So instead, add some central equations for your favorite primitive, favorite invertible quadratic function that make the choice of vinegar variables actually deterministic. So you can actually recover uniquely a pre-image. Okay, so the benefit of this is, as I said, we have a lot of knowledge about the multivariate signature schemes. Multivariate schemes are a lot more successful in signatures than it does in multivariate in encryption. So the security of this shell that you're putting your favorite invertible quadratic map in, that is understood very well. Another benefit is you don't need to add so many equations. We can actually use this construction so that we don't have this factor 2 blow up between plain text and ciphertext, so you don't necessarily have to have such large ciphertext. But a drawback is this is not an actually original idea. This idea came around a long time ago, and most of those schemes were broken. In particular, triangular schemes, this moon letter, for example, is basically this idea, although it was a very, very simple invertible map. Okay, so the star RP constructions, again, this is abstracting away from our selection of that primitive. The idea that we have for this construction is to use unbalanced oil or vinegar or rainbow as a platform for building your scheme. Use the plus modifier, so that's the P, so the R in R, this comes from rainbow. The P comes from plus. You add random central equations. That's to add noise. And also increase the number of equations for min range. And then drop in your favorite invertible central map star. So here is how this construction is actually derived. You fix a bunch of constants. So D, which D is the number of variables that your central map star uses. O, which is number of oil variables. R, which is the number of extra equations in the rainbow layer. And S, the number of plus polynomials. With these parameters, you get a number of variables N, which is D plus O, and a number of equations M, which is D plus O plus R plus S. And so you can play with these constants to get whatever ratio you want between N and M. Okay, we also need to construct a finite field. We're going to call it lowercase k. That's a base field. And a degree D extension k, because we're going to do a big field scheme. Then you construct also your favorite basis of this extension field over the base field, and explicitly define a vector space isomorphism relative to that basis. Okay. So the critical layer of this scheme is some efficiently invertible quadratic map that I'm calling F star. Okay. From the extension field to the extension field, so we're doing a big field scheme. The rainbow layer, if you look at the red variables here, these are the vinegar variables. So these are the vinegar indices, 1 through D, and these are the oil indices. The vinegar variables in the rainbow layer they are the only ones that occur quadratically in the map. So over here you can see in red, it's kind of hard to see on this projection, but these are red. These are vinegar variables, so we have terms that are quadratic in the vinegar variables. And over here, the oil variables only occur linearly in these terms. So if you know the values of the red variables, you can solve explicitly for the values of the black variables. Okay, and that gives us our other portion of our central map, FR, okay, which is O plus R maps. Okay, from the base field raised to the power of n to the base field raised to the power of O plus R. Okay, and then finally you have the plus layer. So the plus layer are random polynomials. These are completely random polynomials in your input variables. And I missed a prime there. I cannibalized some slides from Dr. Ikematsu, and I didn't take out the n prime. All right, so here is what the central map actually looks like. You have an input, which is n variables over the base field. You have phi prime, which is projection onto the first d variables, and then your vector space isomorphism to the extension field. Okay, so that's this map. And then you just have identity here for 2 other copies of k to the n. You run your map F star on the extension field. You run your rainbow map through the center, you run your plus polynomials down here at the bottom, then you combine the answers. This phi inverse prime means apply phi inverse to k to get lowercase k to the d, and then add a bunch of zeros to the end. And that goes in here. You add these components together, and you get an output that's of dimension m over the base field. So the central map is just 3 maps layered one on top of the other. You have your star map expressed over the base field, then your rainbow layer, then your plus layer. Okay. So it is easy to invert this map under the assumption that f star is easily invertible. So if I want to solve the equation f of x equals z, here z is red, indicating that it's a known value. Then the first step is to solve just the f prime part. So what you do is you take the first d components of z, you apply phi to them, actually, to lift them back up, apply f star inverse, and then phi inverse to recover x1 through xd. So after you solved for x1, xd, those become known, which is why they occur in red font down here in the bottom. So then you solve the rainbow layer. These red values are now known, and you can see we only have linear stuff and unknowns. The black variables only occur linearly, so you're able to solve for the rest of the input variables. Okay. So very, very simple to invert. Very simple process. It's exactly like inverting unbalanced oil and vinegar, except instead of randomly choosing your vinegar variables, f star gives you your vinegar variables. Okay. So, how do you build a secret key and public key from this? It's the generic construction. Take some, we're just saying linear maps here. You can do affine maps, make it general. But linear maps and compose to mix up the inputs and the outputs. Okay, so the public key is just the composition of these functions. All right, so SRP is of this flavor. It's just the choice of the f star map is the squaring function. So it's the squaring function over your extension field. You choose an odd characteristic and do your squaring map. Okay, because you don't want it to be linear over base field, right? So you use an odd characteristic. Okay, so we have the squaring map, and you note that if I express this over the base field, then it's still quadratic. This is the generic big field construction. Now, just like Albrecht said in his talk before, there's a relevant algebra in all this algebra A. So you define this representation of the extension field here. I wrote E, it's supposed to be a capital K. You take a representation of your extension field where you just represent every element as the Frobenius powers, all the Frobenius powers of it. And then any quadratic map over the extension field, which looks like this, you can express as this quadratic form, matrix representation of quadratic form. Okay, and that's relevant because that's how you compute the Q rank. And if we look at this matrix for the squaring map, it looks like this. It's 1 with a bunch of zeros. And so this thing is going to have a Q rank of 1, which is very, very low. Okay, and because of that, we were able to do a rank attack. This was last year at SAC. The complexity of this attack on the public key of SRP, it still has a min Q rank of 1. The complexity of this attack is given by this. This is assuming sparsity of the system of equations. That's why we get this figure. We're assuming that it's sparse at every step of the Grosvenor basis calculation, so that we're using sparse linear algebra techniques. If you don't believe this, which is perfectly fine and possibly true, then replace this 2 with your favorite linear algebra exponent, and it'll be okay. So the point is, it's very fast. I think we broke the 80-bit parameters. How fast was it? It was maybe, the 80-bit was like, was it seconds or minutes? I can't remember. The 128-bit, I think, was maybe minutes, if I remember. Very fast. Like, we started running this, and we started talking, and then, oh, up pops the answer. So we were really surprised at how fast it was. Okay, so, but that's just because the bin rank is so low in the central map, the squaring map. So the clear thing to try is to replace it with something that has higher Q rank. So we know that HFE has higher Q rank, and we know how to invert it. So we'll give it a try and see if we can play with the parameters to make it efficient. So that's what we do. So here's HFE. You choose a degree bound D. You generate quadratic terms whose degree is bounded by D. Makes it easy to invert with Berlekamp. And it has a Q rank that is related to the log base Q of D. think I have that on the next slide. Here is what this looks like over that algebra A. You have an upper left block of non-zero values. Okay, and so this one, it's indicating a rank of, this is, I'm calling it lowercase r here, although that's bad notation because we use lowercase r to mean something else in the paper. Okay. It is a necessary condition for HFE that the positive integer d, the degree bound, is chosen so that this polynomial can be solved efficiently by Berlecamp's algorithm. And it's a pretty tight restriction because Berlecamp's algorithm is roughly cubic in d. There's some other terms that can be dominant depending on your parameters. Okay, so the central map for our construction, we constructed HFERP. The central map is the same construction as before, except we drop in HFE as a central map instead of the squaring map. Generate the public key exactly, exactly the same way. Okay, so let's look at the attacks briefly. We have three classes of attacks that we look at, and we look at different versions of these in the paper. So we're using odd characteristic for our construction, so let's go ahead and assume odd characteristic for simplicity. And establishing notation, we'll just call Q1 through Qm the public quadratic forms. Okay, so the min Q rank of HFE hidden right behind this box, right here. Min Q rank of the central map of the HFE is the floor of log base Q of D. And because there's a linear combination of the public maps that give you exactly this map, FHFE, that is going to be an upper bound for the min Q rank of the public key for HFERP. So we know then that the min rank attack is going to have this complexity. We just replace the one that we had before with SRP with the rank of the central map here. Okay, so we need to choose our parameters such that this quantity is high. Okay, so if we look at the direct attack, the complexity is dependent upon the degree of regularity. You might argue that the complexity is related to the solving degree, and that's not a false statement, but for being paranoid, we should maybe say that it's related to the degree of regularity, because once we hit the degree of regularity, we don't think that the matrices are going to grow at the same rate that they do before as we get to the solving degree. So it's a better quantity to focus on for analyzing security. Okay, so the degree of regularity for HFERP, we know is bounded by this quantity because we have a linear combination of the public maps that give us the HFE central map. So we can just apply a theorem from a paper of Gentai and some other authors a few years ago that came up with a degree of regularity bound for that. So we know this is a bound for it. But the complexity of the algebraic attack then is given by this if you're optimistic and assume that your matrices stay sparse in your calculation. Okay. Then because our construction involves UOV or rainbow, we also are vulnerable to every attack that those schemes have against them. And they have several rank attacks that are related to just base field attacks. So there's a min rank attack, dual rank attack, high rank attack. They have all of them. So min rank attack, to focus on that one, we're trying to find vectors Wj satisfying this relation with dgi being the differential of the ith public map. Okay, we have an argument that says that even though we have more equations than variables, we can still with some guessing, get it down to where we only need to solve one set of this equation. So that is, pick only one Wj instead of two, as you might suspect. That makes the attack more efficient, and we estimate the complexity to be this, at least for the class of parameters that we're interested in. In the paper, we have a horribly awful formula that encompasses basically all the cases. You can look at the paper and see the giant branching into the cases. Okay, we also need to consider dual rank or high rank attacks. So the high rank attack in particular is finding linear combinations of the public polynomials that give you a result that's in the span of only the HFE maps and the first layer of rainbow maps. Okay, so they don't have necessarily really low rank but they don't have full rank either. And the complexity for the types of parameters that we're suggesting is of this order. Again, we have a branching out into different possibilities because we have lots of parameters in the scheme. Okay. Here are some suggested parameters. I don't know why we need the 80-bit ones, but we did it. It's just a common thing. It's good for comparison to older schemes to have 80-bit parameters. Here are 128-bit security parameters suggested, so these give us the sufficient amount of security for all these attacks. You'll notice that the 128 ones, we used a rainbow construction. We have 2 oil layers. Okay. We did a bunch of experiments, which are extremely not optimized. We performed these calculations with Magma. So don't believe that this is the best that we can do. But here are some results. So here are results on security. This is very tiny up here, but it had to be for me to fit everything on the slide. This is supposed to show that for various small scale parameters, that the degree of regularity of HFERP is pretty closely related to that of random systems, and that the solving degree is very closely related to the solving degree of random systems, and that both of those correspond to the semi-regular degree for systems of that size. Okay. On the next slide, we have more experimental results. I'm running out of time, it looks like. These are on the rainbow constructions. So it's the same thing, but for the rainbow constructions. The first one was for UOB constructions. Same behavior, very similar to random systems. And here are some performance data, but again, don't believe that these are wonderful. These are not optimized. These are with Magma, a lot of overhead in this. I mean, we can be pretty sure of the secret key size and public key size, don't get me wrong, but these timings are probably not the best that we can do. On the other hand, I don't know that we can do a lot better either, but it's not the best we can do. Okay. And where do we go from here? It'd be nice to come up with some improvements of this. One way to do that would be to replace HFE with HFE minus, because paper last year showed that HFE minus is HFE. It's just more efficient. And another direction to go is, how do we break this thing? I'm hoping to get a lot of new science out of this. I'm hoping to inspire something. And with that, I'll terminate and hopefully, well, I don't think we have time.